The very first factoring technique that we are likely to use in any given situation is the one that you would have had to use to answer question 3, which asks you to factor the expression 9y squared minus 15y cubed. So what was your approach? How did you begin the process of factoring that expression, Robert?
Find the GCF of 9 and 15.
Exactly. So GCF is the first line of defense in any factoring problem. Is there something that you can take out, something that all of the terms in this polynomial expression have in common? If there is, we should take that out first. So Robert started by asking, what is the GCF of the two numbers, 9 and 15? How'd you find it?
Well, I know that 3 goes into 9 3 times, and 3 goes into 15, so, and there's no more, like, there's no greater than that.
Yeah.
Oh, yeah.
So you notice that both 9 and 15 have this common factor of 3 in them, and that's the most that these two numbers have in common, right? Because the remainder, 3 and 5, don't have any non-trivial factor in common, right? Only one, because they're both prime numbers and they're different. So the greatest common factor of the two numbers 9 and 15 is 3. So we know for sure we're going to be able to take a 3 out of this expression. I'll write it this way, it's 3. So for sure, when we factor this, we're going to be able to pull a 3 out. So I'm going to write that right away. I'll be able to pull out a 3, and then I'll have some parentheses here, and I'll have some stuff inside there. But I want to soup up this question a little bit more, because sometimes you're asked this outright, sometimes you have to kind of worry about it on your own. But what if I alter the question so that I want to know not what is the greatest common factor of those two numbers, 9 and 15, but what is the greatest common factor of the two monomial expressions, 9y squared and 15y cubed? How does that change your thought process? What would be the greatest common factor of those two expressions? What's the most that those two expressions have in common? Yeah? 3y squared. And why y squared, or how come y squared is a part of this greatest common factor?
Because y squared is y times y, and y cubed is y times y, so they have y times y in common.
Yeah, we could play the same sort of factor tree game, including the y squared as y times y, and including the y to the third as y times y times y, right? We can include the variables in our factorization process. We sort of treat the variables as though they're just like other prime numbers in our factor tree. And according to what Gabby just said, that means that we can identify that both of these expressions have actually two factors of y in common, right? So the greatest common factor between these two expressions is not just 3, but it's 3 times y, otherwise known as 3y squared. Does anybody see the shortcut, by the way? If I have two monomials, how do I decide how many powers of y belong to the greatest common factor between y squared and y cubed? What did we end up choosing? The smaller, the exponent that was smaller. So that's a quick shorthand rule of thumb. Choose the smallest exponent on each prime factor and variable. On each variable. And if you're working with prime factorizations, you can also choose the smallest exponent on each prime factor. And that's what goes into the GCF. So 3y squared is the greatest common factor of these two monomials, and so that's what we're going to factor out of this expression. If the question had only asked you to find the greatest common factor, we would be done. We would say 3y squared, and we would move on. But the question asks you to factor, as a verb, this expression. So what else do we have to do before we're finished?
Factor 3y squared into that problem.
Factor 3y squared out of that expression. Ken, were you going to add something to that? Okay. Yeah, right. So now we have to actually accomplish this factorization. So the question now is, how do I undo the distributive property? In the sense that if I were to re-multiply this expression back out, how could I ensure that what I get is my original expression, 9y squared minus 15y cubed? How do we figure out how to fill in these empty parentheses? Robert?
You divide 3y squared from 9y squared in
that happens to be my preferred way of looking at this problem. Right. Sometimes people will look at it and kind of ask themselves, all right, what's missing between 9y squared and 3y squared? What's the difference? And that's a little bit dangerous sometimes, because when you start thinking about differences, you often think about subtraction, when really subtraction is not the operation we're worried about here. It's really division. Because what we're doing is undoing multiplication, it makes sense that that would involve a process of dividing. So what's left over inside these parentheses is exactly what Robert says. It's the result of dividing the original quantities, the original terms, 9y squared and 15y to the third, by the greatest common factor that we are endeavoring to factor out here, which is 3y squared. So now we have a couple of division problems that look an awful lot like the division problems that you confronted in Module 6. Because they're going to require me, for example, to ask, in the second term, how do I divide y to the power 3 by y to the power 2? What do we do to accomplish this division? How many y's do we end up with there? Okay.
You would subtract it. I usually do 3 minus 2 because it's a division line.
Yep, exactly. So according to our exponent properties from the previous module, when we divide two powers of the same variable, their exponents subtract. So the number of y's that I'm going to end up with in that second term is y to the power 3 minus 2, otherwise known as y to the power 1. And we don't need to write a power of 1 if we don't want to, so we can leave that as just plain y. What about in our first term, where I have y squared divided by y squared? How many y's do I end up with? No y's at all, right? So that term, when I do my division, is no longer going to have a y in it. But instead, what's going to be left over in that term is the result of dividing, 9 by 3. And 9 divided by 3 is going to give me a 3. And then 15 divided by 3 is going to leave me with a 5. And that, then, is the factorization of this expression, factored as completely as possible. We'll know that we've factored it as completely as possible if there's no greatest common factor between the stuff that's inside the parentheses anymore. The greatest common factor between 3 and 5y is nothing interesting. It's just 1. 3 and 5 have nothing in common. And the number of powers of y, the smallest number of powers of y in these two terms, is no powers of y at all. So there's nothing in common that 3 and 5y have that we can continue to factor. So we know we're done at this point. And you can always check your answer by multiplying this back out and verifying that what you end up with is what we started with. 3y squared times 3 would be 9y squared. 3y squared times 5y would be 15, y to the 2 plus 1, y to the 3. And that's exactly what we started with. Factoring is a trick. Unfactoring is a process. It's a recipe. So anytime you have an answer to a factoring problem, it's a good idea, if you have the time, to check it by multiplying it back out and verifying that you get back to the thing that you started with. Because if you did, you at least have a correct factorization. It may not be the most complete factorization, but it definitely is one that works.